Good morning, everyone. And in this third video of lecture series of Theory of Computation, we are going to discuss about conversion of NFA to DFA, that is non-deterministic finite automata to deterministic finite automata. So the question arises that what is the need of conversion of this non-deterministic finite automata to deterministic finite automata? So as we studied in last lecture, that a non-deterministic finite automata is a machine where the condition of non-determinism exists. That means we do not have a clear idea of which transition is to be followed or which transition is to be executed to get the ultimate result. So such kind of machine in such kind of machine there is a ambiguous kind of situation which cannot be implemented directly into the in any programming language. So to convert such machines into or to implement such machines in any programming language, we have to convert those non-deterministic machines into deterministic ones. So as it is written here over here, that for every NFA there exists a DFA. So this is a theorem that whether there is any non-deterministic finite automata you construct, there is a DFA that will be existing for that machine. So what are the steps to convert those NFA to DFA? So you have to start. I'm enlisting the steps to convert such machines. So first of all, I have to find out the epsilon closure of initial state. By epsilon closure of initial state, I mean that on giving epsilon, that is null string to your initial state of the machine, given machine, what is the result? Whatever the result you get, make it as your initial state of the DFA machine which you are trying to find. The next step is to let us suppose that you have got two input alphabets, 0 and 1. It will differ from problem to problem and situation to situation. If you have got small a and small b as input alphabet, then you have to find their closure. But if you have suppose 0 and 1 as your input alphabet, for I've just written it here for your understanding, that you have to find 0 closure and 1 closure for the existing state, whatever state you have found out just now. So you have to by 0 closure and 1 closure, I'm again telling you this thing, that by 0 closure I mean by on giving 0 to that existing state, what are the possibilities of transition, where what are the states where we can reach. And by 1 closure, I mean on giving 1 to that particular state, what are the possibility of transition. We will continue this step, will be repeating step 3 until the new states are being obtained. We'll stop once we'll stop getting the new state, and then we have to decide the final state of the DFA. So final state of the DFA will be the state which will consist of the final states of the question NFA machine. Okay, so these are the steps listed here which you have to remember while converting an NFA to DFA. Now I will make you understand this concept by taking an example. So let us you've got a question that you have to design a DFA over sigma is equals to a comma b. That means input alphabets are small a and small b, such that it accepts all possible strings of a and b that ends with ABB. That means all possible strings of a and b will be accepted. Those are having ABB at their trailing end, at their tail. If they have ABB at their tail end, then it will be called as valid string. Rest of the all these strings will be discarded or will be termed as invalid. Okay, so we have to construct such a machine. So what we have to do, we have to first of all we will try to make a finite state machine. We'll not keep it that thing in mind that we have to make a DFA or NFA. Whatever machine we'll get, then we'll proceed to the next step. So first of all, I'll make an initial state. There is a initial state in every machine. So I will make initial state, the very first step. Then for making or for accepting any possible combination of A and B, what I'll do, there will be infinite combination of A and B. Any number of A's, any number of B's, or any number of A followed by B or B followed by A, anything can happen. So I will make that thing by these two self loops of A and B. By these two self loop, I can make any possible combination of A and B. But the condition of the question is that the machine reaches to the final state, or will say valid, whenever the tail end has ABB at its end. So what I'll do, I will take A and reach to Q1, then B and reach to Q2, and then B again to reach to the final state Q3. So our machine is reaching to the final state once it has read ABB at its end. Okay, so this is the simple logic of preparing for constructing a machine. But now, as you can see, that in this machine there is a problem, that on giving small a to Q naught or Q0, what is happening? We are coming back to Q0 itself and Q1 also. So there are two paths or two transition for small a from Q0. So this is a clear-cut case of non-determinism, and this is a NFA. So what we have to do, we just have to, since we cannot implement this machine, what we have to do, we have to convert it into a DFA. Now I will take help of those steps which I have told you here in last slide, and will convert this given NFA into equivalent DFA. There will be no difference in the language accepted by both the machines. The only difference is that these condition of NFA will be eliminated from here. Okay, so let us start with the first step, that is find epsilon closure of initial state. So epsilon closure of initial state, that means Q0. If you can see Q0 here, if we give a null string here, or in another language, if I say, if we give nothing to Q0, where will we can make the transition? So the answer is Q0 itself. You can go nowhere. If you are getting nothing, you are going nowhere, because all the output arrows, if you see, all the output arrows are leading to somewhere by taking some input. There is no epsilon transition here. So epsilon closure of Q0 will be Q0 itself. So what will happen? Q0 will be our initial state of the required DFA. So let us make an initial state of our answer machine. So this is the initial state of DFA, which we are trying to make out of this given NFA over top of this slide. So now what? Now I will, now I have Q0 as my existing state. So what I'll do, I will find A closure and B closure for this state. Okay. So, and we'll repeat this step until unless I stop getting the new state. Okay. So what I'll do, I will find out 0 closure and 1 closure for the existing state. So existing state is Q0. So what I'll do, I will find A closure of Q0. So what can I get after giving A to Q0? I can reach to Q0 and Q1 both. So I will write Q0 and Q1 both here. If you can see, I have written both the things here. On giving A to Q0, I can reach to Q0 and Q1. Okay. Similarly, B closure, on giving B to Q0, what will happen? I will reach to Q0 only. Right. Now I will trace out this steps which I have calculated just now into my machine. So this is the portion which I have made in the last step. Now what I'll do, I will make a transition of A, which will lead to a new state Q0, Q1. Now do not bother about the state name written here. It can be renamed on the later stage. So what I have done, on making a transition, I have reached to Q0, Q1, and on making B closure, what will happen, I will reach to Q0 itself, because B closure of Q0 is Q0 itself. So a self loop will be made from B. Now what is the new state we have got? Q0, Q1. So what we will do, we'll find 0 closure of Q0, Q1 and 1 closure of Q0, Q1. The same step will be repeated again and again until we will be getting new states. So let us repeat that step again. So what I have done here, I have given small a to Q0 and Q1 collectively. Okay. So on giving a to Q0, what is happening? I'm getting Q0 and Q1. So I have written Q0, Q1 here. On giving a to small a to Q1, what is happening? It is leading us to nowhere because there is no transition of small a from Q1. So the answer will be Q0 and Q1 itself. Okay. Now, next is B closure. So on giving B to Q0, what is the answer? I'm reaching to Q0. So I've written Q0 here. And on giving B to Q1, I'm reaching to Q2. If you can see in this machine right over the top of this slide, on giving B to Q1, I'm reaching to Q2. So answer is Q0, Q2. So I will trace out these findings in my machine. So this is the machine which I have made in the last step. Now, what will be happening on a transition from Q0, Q1, I am reaching to Q0, Q1 only. So there will be a self loop. And from Q0, Q1 on giving B, I am reaching to some state Q0, Q2. So Q0, Q2 is not present at this moment. So I'll make a new state Q0, Q2 and make B transition for it, right? Now, I've got a new state Q0, Q2. So I'll repeat the same step for this Q0, Q2 state also. So I will find A closure of Q0, Q2 and B closure of Q0, Q2. So if you can see here, on giving A to Q0, I am getting Q0 and Q1. And on giving A to Q2, I'm making the transition out to nowhere because Q2 does not have any A transition. So the answer will be Q0 and Q1 only. Now on giving B to Q0, Q2, what is happening? Q0 on getting B will reach to Q0. So I've written Q0 here. And on giving B to Q2, if you can see here, I'm reaching to Q3. So I've written Q3 here. So one new state is found in this step also. So what I'll do, this is the machine which was made by me in last step. Now what I'll do, I'll make an A transition, which is leading me to Q0, Q1. As you can see, Q0, Q1 is existing in my machine. So I'll not make it separately. I will use that state again and will make this A transition to Q0, Q1. Back to that state, and from Q0, Q3 on taking B as input, I will reach to a new state Q0, Q3. Now this step will be repeated again. So on A closure of Q0, Q3 will be Q0, Q1. How? Q0 on getting A as input, it will be giving us Q0 and Q1. As you can see, on giving A as input to Q0, I will reach to Q0 and Q1. So I have written here Q0, Q1. And on giving A to Q3, I'm getting nowhere because there is no outgoing transition from Q3. So the answer will be Q0, Q1 itself. B closure of Q0, Q3 will be on giving B to Q0, the answer will be Q0 only because the self loop of B is leading us to Q0. So in answer, I've written Q0. And on giving B to Q3, if you can see, there is no outgoing transition or no transition of B from Q3. So I will write nothing except Q0. So answer is Q0. So this is the machine which I made in up to the last step. Now I will trace out these findings which I have found in step 4 here. So the for A closure, I will make as a back loop to Q0, Q1, and for B, I will make a transition to Q0. So in this step, if you can observe, there is no new state found because I've reused the existing state. On A transition from Q0, Q3, I've reached to Q0, Q1, and on B transition, I've reached to Q0. So no new state has been found here. So I will stop here only. my machine is about to complete. Now I have to decide what are the final state of my machine. So in the question machine, if you can see, only Q3 is the final state here. So wherever Q3 is coming in this answer machine, will make that state as final. So there is only one state where Q3 is appearing, that is Q0, Q3. So we'll make this state as final state, and this is the machine which will be called as equivalent DFA of that machine which we have drawn in the first step. Both the machine are equivalent. There is no difference in the language accepted in this machine or the machine which was given in the question. So this is the way how to convert an NFA into a DFA. Now I will try to explain you a method by which you can convert an NFA with epsilon move to DFA. The steps are exactly same. You have nothing new to learn. Just you have to trace out the transition properly. So if I make you recall this concept of NFA with epsilon move, so this is nothing but an NFA with which can be defined with 5 tuples, that is Q, sigma, del, Q naught, and F. Q is the set of state, sigma is the set of input alphabet, del is the transition function, and the transition function here is slightly different from the NFA, where in the input alphabet you are considering a special symbol which is known as epsilon or null string. On the right hand side, you are writing 2 to the power q. That means maximum possible combination of states where you can reach after reading the present state and input symbol. Q naught is the initial state and F is the set of final states. So this was the formal definition of NFA with epsilon move. This was discussed by me in the last lecture also. Now in a brief, I will discuss how to convert an NFA with epsilon move to DFA. The method is very much same. There is nothing different in it. If you can see in the first, after starting, the first step is to find the epsilon closure of initial state and make the result as initial state of your DFA. Let us suppose sigma is equals to 0, 1, means let us suppose input is 0 and 1. It can be different in your case that you are solving. But here, if you consider it is as 0 and 1, you have to find 0 closure and 1 closure for the existing state. And then you have to repeat the step number 3 until you are getting the new states. Once you are stop getting these new states are not found, what you have to do, you have to decide the final state, and the final state will be the states which will be consisting the final states of the NFA machine. And in that way, you can convert your NFA with epsilon move to a DFA. We can understand by this concept by a small example. So here is a machine which is you can see there are epsilon transition in it. So you can clearly state this machine as NFA with epsilon move. Now we have to convert it into an equivalent DFA. So how to convert it? First of all, you have to find the epsilon closure of initial state. So epsilon closure of initial state will be for epsilon closure of initial state, that is A will be ABC, because if you can see on A, if I give nothing to state A, means no input alphabet is given to state A, what will happen? It can either stay at A, it can reach to B, or it can reach to C, because there is the control has has to make no efforts in reaching to state B or state C. So answer will be A, B, and C. So ABC in our case will be our initial state. Okay. Now I have got ABC as my initial state. What I have to do, I have to find out 0 closure, 1 closure, and 2 closure, because if here you have got 3 input alphabet, 0, 1, and 2. So you have to find 3 closures: 0 closure of the existing state, 1 closure of the existing state, and 2 closure of the existing state. So 0 closure of the ABC will be ABC again, because as I told you in previous lecture, that on giving 0 to A, where we can reach, what are the possibilities? On getting 0 from A, we can reach to A directly, And after reading A, either we can rest at A, or we can reach to B without making any effort, or can reach to C without making any effort. So what is the answer? On giving 0 to A, we can stay at A, we can stay at B, or we can stay at C. So answer will be A, B, and C. So the same thing is written here also, that zero closure of ABC will be equals to ABC. Now, if I say about one closure of ABC, what will happen? One closure of ABC will lead us to BC, because from A, you cannot take directly a zero transition, but you can reach to B by an epsilon transition, and then you can make a one transition and will reach to B. And after taking one, you can either rest at B or move to C with the help of epsilon transition. So answer will be B and C. So the same thing is written over here, and similarly you will find out the two closure of ABC which will be equals to C, and you will be tracing out all these three calculation in your machine. So 0 is the closure of ABC is ABC, so I'll make a self loop over here. Then one closure of ABC will lead me to a new state BC, so I'll make a new state BC and will make one transition. And for 2, I'll make another new state C, and I will trace out the transition for 2. And similarly, as I got two new states here, BC and C, I will repeat this step again and again till no new state is found. So this is the final machine which I'll get. And lastly, I have to make the final state. So for making final state, what I'll do, I will make those states as final state which are consisting the final state of given question machine, and that is C. So C is there in every state here. So I'll make all three states as final state here. So in this way, we can convert NFA with epsilon move to DFA. The method is very much same. You just have to use the same steps to convert an NFA to DFA. The only difference here is to trace out the transition, how to make the transition, and how the epsilon as input alphabet is affecting your movement from one state to another. So this was all about the conversion of NFA to DFA. In next lecture, we'll be going through the minimization of DFA. Thank you so much.